started. I have the honor of introducing John Evans, Professor John Evans from CU Colorado, University of Colorado Boulder, CU Boulder. John's well known for research in a wide range of areas. He's going to be talking about one of those today, immersed finite element methods. But in addition to that, he's done work in stabilized finite element methods, so discretization focused work. He's done work in turbulence modeling, data-driven turbulence modeling, large eddy simulations, isogeometric analysis, a whole range of things. So he's here through tomorrow, and there's a little bit of time on the schedule too. So if at some point you'd like to try and meet up with him, you could certainly reach out to either myself or Zhao, and we can try to pop you on the schedule as well. So the other thing I would say is I've had the privilege of working with John. I spent a year at CU Boulder on sabbatical, which was great to get a chance to see some more of the work that he's done in detail. So he did his PhD at UT Austin and did a postdoc there as well as part of what's now known as the Odin Institute, and worked with Tom Hughes while he was there, and has been at about 10 years now at CU Boulder. So with that, thanks, John, for coming, and look forward to hearing your talk.
Excellent. Thanks so much, Dave, for the introduction, and thank you all for coming here today. It's an absolute pleasure. It's funny, you mentioned now 10 years at CU Boulder. I like to think of myself as being that young person. I no longer can say that. It's also been 10 years since I've been to MIT, so it's really great to be here today. So the title of my talk here today is actually quite ambitious. Immersed finite element analysis, opportunities, challenges, and recent advances. And it turns out that immersed finite element analysis is a huge research area, and I'll explain what immersed finite element analysis is here in a minute. And while putting together this presentation and describing various challenges and recent advances, I realized that this would be a 14-hour talk. And I don't think anybody wants to be here for 14 hours. So what I'm going to actually do today is I'm actually going to narrow down on one particular challenge associated with immersed finite element analysis, and that is actually implementation. So if any of you played with immersed finite element analysis before, you might note that, sure, maybe you can write down the discretization on paper, but when you actually try to go from paper to code, it's a big pain in the neck. This actually inspired us to try to answer the question, is there a way that we can convert classical finite element codes, such as Phoenix, into immersed finite element codes? And you'll see why we might want to do that here in a minute with minimal human effort. And it turned out that using existing paradigms, this is not really quite possible. So instead actually led us to develop new methodologies. We actually developed a new software platform to enable this as well. So I want to highlight some of those features here today, and leave things such as linear system solution, nonlinear system solution, quadrature, et cetera, for another day here today. So with that in mind, perhaps a better title for today's talk is the Exhume Project for Democratization of Immersed finite element analysis. And democratization is kind of a buzzy word, which here I just mean to make immersed finite element analysis available to a wider range of practitioners. So of course, like any research, this was not done in a vacuum. So the Exhume project is actually a joint effort between the University of Colorado Boulder and UCSD. This is a funded project through the NSF CSSI program. And at CU Boulder, there's primarily 3 folks working on this. So myself and my close collaborator, Professor Kurt Monte, and our PhD student, Niels Wunsch. And then from UCSD, the original project team was David Kamensky. So he was an assistant professor in mechanical engineering at UCSD. And the primary student driver there was Jennifer Fromm, and Ru and Han were also PhD students on this effort. So just to highlight, those are the 2 main players in today's talk. Well, David, it turns out, decided that he could make a lot more money in industry. So in April, he actually left UCSD and joined Conform as a senior software engineer. And the new PI on the project is JS Gen. And here we've actually been trying to extend ideas I'll talk about here today for immersed finite analysis also to meshless methods, so things like reproducing kernel methods, trying to think about problems that are very hard, such as soil structure interaction and the like. So some of the ideas I'll talk about here today, we're starting to investigate in those contexts. In this last summer, we also had an undergraduate join our lab, Ryan Caputo, and what he actually did is, without any prior training in finite elements, managed to convert a classical educational MATLAB-based finite element code to an immersed code by the end of the summer. So actually learning what finite elements was, going all the way to completion, and actually that has higher order capabilities, curved elements, and the like. So it was actually quite impressive what Ryan had done. So as David already mentioned, Dave visited us at CU Boulder for a year last year as part of a sabbatical, and I wanted to just make a plea, please come visit us. We love having people in Boulder, Colorado. So CU Boulder is located in Boulder, which is right at the edge of the Rocky Mountains. So this mountain here is Bear Peak and Green Mountain. We actually have 5 big peaks in Boulder. There's something called the Boulder Traverse. If you're crazy, you want to go for a 20-mile run, you can try to hit all of these in a single day. But it's a really fun place to come and visit and go hang out in the mountains or go hang out with us in Smead Aerospace. So I'm part of the NNHJ Smead Department of Aerospace Engineering Sciences, and we have a lot of folks specifically working in the area of computational mechanics. So we have, for instance, Ken Jansen, my close collaborator, who works on unstructured CFD, Kurt Mate, who I mentioned before, who's an expert in topology optimization, Alareza Dustin, working on uncertainty quantification, et cetera. So please come visit. And we have a new building with some fun, fancy murals. So Dave got to hang out there for a year, so he can maybe tell you the good and the bad about CU. All right, so without further ado, let me go on to part 1 of my talk, which is motivation. And here I'd like to introduce why are we interested in immersed finite element methods, what roughly are immersed finite element methods, and what is that particular challenge that I alluded to earlier in terms of implementation. So I'm going to assume something here, that people have seen classical finite element analysis in some way, shape, or form. But the basic idea, if you recall, behind classical finite element analysis is you've got some system you're interested in analyzing. Say you're interested in looking at the structural deformation of an aircraft wing, right, under some loading, right, from the air going around that wing. And in order to actually solve the equations that govern the structural deformation of that wing, what we typically do in classical finite element analysis is basically decompose the wing, right, into a bunch of elements, right, or cells, right? These could be tets, they could be hexes, they could be pyramids, wedges. And then we discretize the governing equations by representing the solution field we're interested in, for this particular case, displacement, in terms of a sum of coefficients times finite element functions, finite element basis functions, right, over that mesh. So these are piecewise polynomial functions. So in this process, we have to generate a high quality body fitted finite element mesh. So that means that the mesh actually will adhere to the geometric boundaries of the domain. And if you got multiple materials, you also have to adhere to material interfaces as well. And for complicated applications, such as you're analyzing, for instance, structural deformation of a nuclear submarine, this can be an extremely costly process. And there was a study done by Sandia National Laboratories as part of the DART study about 15 years ago that actually showed that upwards of 80% of the time that's needed in going from a design to analysis was not dedicated to finite element analysis per se, but to pre and post processing. In particular, you can see that we got a huge chunk of time here going from this conceptual design model, right, to finally having what I refer to as an analysis suitable model, right? And this is obviously not ideal. And this is especially true for geometrically complex multi-material, multi-physics problems. So some problems that we're interested in my group, for instance, is modeling heat transfer and heat exchangers. And here, typically, you've got a coupled thermal fluid simulation that you actually need to conduct. So this is an example of a geometry that's described what's called an FREP So function representation by end topology. Down here, we have a fiber composite structure, right? Where you've got multiple materials, right? You got these fiber inside of an epoxy. And then you've got a 3D scan of a bone. And you can see these bio problems, right, can really give rise to very complicated geometries. And trying to mesh this with a high quality mesh can take some time. So Dave mentioned I've done some prior work in isogeometric analysis, and I would contend that's my most highly cited work is from the isogeometric analysis community. And the idea behind isogeometric analysis is instead of trying to mesh your object, right, and then trying to represent solution fields that you're interested in as a set of coefficients times piecewise polynomials on that mesh, instead, let's try to use the basis that's already used in computer-aided design, or CAD, directly for computer-aided engineering, CAE, right? In this bypass the need for the generation of a high-quality body-fitted finite element mesh. But it turns out there's a number of problems associated with this, and these are research problems that are being tackled by the isogeometric analysis community, but they're still outstanding. And the primary issue is that isogeometric analysis, at least in its original instantiation, requires an explicit parameterization of the geometric domain. However, it turns out that in many situations, what we do instead is we've actually got some implicit features. And that's due to the fact that we often use trimming. So if you're looking at this object here, typically in CAD, what we do is we represent this as a bunch of patches. And patches you can think of as you take kind of a square parametric domain, right? And you map this with some NURBS surface. So it's a set of three-dimensional coefficients times NURBS basis functions, right? And then you map that onto the physical domain. So that gives rise to this yellow, this red, this purple region, this green, and this blue. But you'll notice, for instance, this purple region, we've cut something away, right? So we often have holes, we often have other features. And it turns out that trying to map a bunch of squares onto those features is not nearly as convenient as literally just taking a pair of scissors and cutting those features away. And the way this is done typically in CAD is you actually will draw curves in the parametric domain and then map that onto the physical domain. And by doing this, we no longer have an explicit parameterization of geometry, but instead you actually have an implicit description of those curves. We also have additional issues. For instance, we often will cut something away like we have here in yellow, then try to paste this green thing on. And what you'll find is the boundary of this green object will not exactly match with the whole of that yellow object. And what you'll end up getting is, for instance, gaps and overlaps. And this can be a big problem for analysis unless you have a notion of what topologically is connected there. So this gives rise to a number of issues in trying to actually utilize isogeometric analysis directly on CAD geometries. And it turns out the problem is actually much more complicated in 3 spatial dimensions. So if any of you are familiar with how volumes are represented in CAD, for instance, in SolidWorks, they're typically represented not in terms of the volume itself, but the bounding surfaces. All right, so you typically have what's called a B-rep, or a boundary representation. So if you've got some sort of engineering object, you've got an explicit parameterization of the boundaries, but you don't have an explicit volumetric parameterization. So my old PhD student, Luke Engvall, used to joke that SolidWorks really should be called SurfaceWorks, as a more true representation of what's going on underneath the hood. So you actually need to essentially mesh, right? Come up with a volumetric parameterization at the end of the day. So the idea behind immersed finite element analysis, and I'll also refer to immersed isogeometric analysis, and you might ask, what does that mean? I'll tell you here in a minute, is another approach. And the idea here is instead of trying to represent the solution field, right, in terms of shape functions that are defined on some body-fitted mesh, instead what we'll do is we'll represent the solution field in terms of basis functions that are defined on some non-body fitted mesh. So you can see an example of that for the case of this propeller here, right? So you can define, for instance, your standard tensor product finite element basis functions that you might be familiar with here. You could use splines, you could use many different things, right? And that then alleviates the need for creating a mesh for representation of those approximation functions, right? You can just use something extremely simple, right? And because of that, it can be directly applied, for instance, to trim CAD geometries and very complex shapes, right? So that surface to volume problem that I talked about earlier, it alleviates that entirely. Now, of course, this doesn't come without its own issues. For instance, as you'll see here in a minute, you need to enforce boundary conditions, right? With classical finite elements, because your elements actually adhere to geometric boundaries and material interfaces, right? And if you're using, say, a Lagrange basis, you can apply boundary conditions directly, right, to nodal degrees of freedom that lie on the boundary. We no longer have such degrees of freedom in this case, so we need to use other technology in order to handle this. And there's some other issues that I'll mention here in a minute. Nonetheless, it opens the door to other sorts of problems that are very hard to tackle, for instance, using classical finite element analysis. So one problem that I've been involved with trying to simulate for the last 10 years of my life is actually simulation of bioprosthetic heart valves. So if you actually think about a heart valve, what happens, right, is the valve will open and close, open and close. And this is an interesting multiphysics problem where you've actually got, right, this moving valve, right? So this moving shell-like structure, right, membrane-like structure, that'll be interacting with the blood flow around it, right? So you've got this fluid structure coupling. And if you actually think about the human heart, you'll typically have the valve walls moving as well, et cetera. Now, the issue is, as the valve opens and closes, the fluidic domain actually changes topology, right? So when the valve is completely closed, right, what you find is, the inflow region and the outflow region are disconnected topologically, right? So basically you have kind of like topology that's equivalent to two cubes or two spheres, right? Well, when it's open, you can actually draw a path between. So if you use classical techniques for fluid structure interaction, computational fluid structure interaction, things like ALE, so arbitrary Lagrangian Eulerian, where elements will actually move, right, as this valve moves, what you'll actually find is you'll end up squishing elements to zero size and actually break your simulation. With immersed methods, on the other hand, what you can do is you can just say, hey, rather than having the fluidic mesh move with the structure, we're going to instead let the valve move through the fluidic mesh. So that opens up a lot of new possibilities in terms of numerical methods. And then the challenge becomes, you've got interface conditions, right, between the valve and the surrounding fluid flow. For instance, the fluid velocity should match the structural velocity, right, along that shell structure. So now you have to think about, how do I do that when we don't have the meshes aligning? So another example of a problem that you can tackle with immersed finite element analysis much more easily than classical finite element analysis is blood cells moving through a blood vessel like a capillary. And every single time, right, that a blood cell will enter in the domain or exit out of the domain, the topology of the fluidic domain changes, right? And you can imagine, even if you don't have any blood cells coming into the domain or leaving the domain, right, as they move from left to right, if you're trying to use an approach where the fluid mesh will move with the structural mesh, you can imagine that you'll get very strong distortion quite quickly, right? And you'll have elements invert and do all sorts of bad things. So instead, it's quite powerful to represent the velocity field with respect to a fixed mesh, right? And have the blood cells move through it instead. So these are some snapshots from a paper by Hugo Casquero. And what Hugo did is he actually employed isogeometric analysis type techniques, in particular using splines for representing the velocity field and the pressure fields of the fluid flow. And he used this particular approach called divergence conforming B-splines. And what he also did by doing that was have a purely mass conserving method, which mass conservation is known to be an issue with immersed methods. For immersed finite element methods, if you choose your spaces correctly, you can actually alleviate this issue, which is quite nice. And what's excited me about the promise of immersed finite element methods the last 6 or 7 years is joint work with Kurt Monte. And really what we're interested in doing is actually optimizing not just geometry, but topology. What you can do, you can imagine, for instance, is suppose I want to create a table here and it's going to support this load, right? And I want to minimize compliance, right? What you can imagine is say, rather than trying to say I've got some predefined notion of shape, instead, let's just say that I can have material at a spot or no material at a spot. And I can try to optimize, right, the material layout to support that shape, right, according to some objective functional constraints, right? And it turns out that computationally you can do this using, for instance, level set fields. So that's typically what we do. So what we do is we use spline-based representation of level sets. And basically what a level set does is if your level set is positive, you have material. If it's negative, you have no material. So the zero level set, in this case, will actually define your geometric boundary, right? And now what you can imagine doing is if I actually represent this level set field, right, as a set of coefficients times three-dimensional B-splines on this bounding box, I can try to optimize the coefficients of that level set representation, right? And that gives rise to an optimization problem that I can run, right? In order to get the structural response now, though, I need to run a simulation, right? Now, as the geometry and the topology keep evolving, you can imagine that trying to generate a high-quality body-fitted mesh every single iteration would be quite expensive. So what we do instead is we actually use immersed finite element analysis to perform those operations. So that is, our background basis functions are always fixed. And in this particular case, we're actually using hierarchical B-splines to locally refine around solution fields of interest, so features of interest, as well as kind of geometric boundaries to better represent, in this particular case, the displacement field and derivatives of it that give rise to, for instance, von Mises stress and the like. We've actually been tackling a lot of different problems besides, structural topology optimization problems, thermal structural problems, low Reynolds number fluids problems, and the like, as well as multi-material. And you can tackle multi-material problems by using multiple level set fields, right, where you can actually represent different materials that you may be interested in utilizing. So it's a very powerful technique that really benefits from using immersed finite element analysis rather than classical finite element analysis. However, all right, so 20 minutes later, I have to take time with motivation, make sure all the students in the room are on the same page. That there is a drawback, and there's a few drawbacks. And one of the biggest issues, as I mentioned on my very first slide, is implementation of an immersed finite element analysis code is a challenging and time-consuming task. And this is true even for domain experts. And the primary issue is numerical integration over cut cells, right? So if you consider this physical domain here that's depicted in gray, so you have this square with a hole in it, but let's rotate it. And then let's say we're going to use a tensor product background mesh. Maybe I'll use B-splines, maybe I'll use classical finite elements, right, for my solution field. If you use an immersed finite element method, what you actually need to do is you need to integrate for each cell the gray region in that cell, right? So for the uncut cells, these untrimmed cells, you can use, for instance, standard Gauss quadrature rules, right? Tensor product quadrature rules. However, when you get to these trim cells, you can no longer rely on that. So you need to account for that. And the issue is that you can really cut those cells in arbitrary ways. So there's not one canonical rule that you can apply to every single trim cell. Now, obviously, immersed finite element methods have been popular for some time now. So there's been many different strategies that have been proposed in the literature. One very common approach is to actually build a quadtree or octree approximation of your gray domain, right, that you have from the previous slide, and then perform Gauss quadrature on this octree quadtree mesh. But as you can see, this can actually generate a ton of quadrature points. What's nice about this is you can use just inside-out queries to be able to build these meshes. Another approach is you can actually just build a mesh. You can tessellate. And you might ask yourself, why even bother with an immersed method if you're just going to mesh? Well, remember, all we're using this mesh for is integration. So this can be actually a very poor quality mesh. at the end of the day, right? And there's ways of generating meshes that are poor quality quite fast, right? So that's actually convenient. There's another class of methods, and I know Dave has worked there, and I've worked there as well, that actually can use Green's theorem to generate quadrature rules without having to parameterize the domain at all. Essentially, what you can do is you can represent volume integrals in terms of surface integrals if you can represent the integrand as a divergence of something. And it turns out that you can actually use numerical anti-differentiation to figure out what that function is. So you can transform volume integrals into surface integrals. And it turns out you can do the same thing. You can iterate and transform surface integrals into line integrals. This requires explicit parameterizations of your surface and those line integrals, which in some cases is possible, in some cases it's not. But in all of these cases, what you end up with is a specialized quadrature rule for every single cut cell. So for every single cut cell, you need to say, okay, cool, let me go ahead and generate a new quadrature rule. And every single time your geometry changes, your topology changes, you have to generate yet another quadrature rule, right? So this is a big pain in the neck. And from a finite element code, that means that I need to be able to actually read in all of these quadrature rules, right? And I need to be able to modify the classical finite element code works by looping over quadrature points. I need to be able to loop over custom quadrature points for each cut cell. And if you looked at, legacy 1970s codes, it turns out a lot of times those basis functions at quadrature points is hard coded. So this is not really something that you can easily do. Or you need a way of recognizing you've got two different meshes that you're playing with, one for integration, one for analysis, and have them somehow communicate. So as you can imagine, this makes implementation quite difficult. So the purpose of the Exhume project is to ease the burden of implementing an immersed code. And in particular, what this project enables one to do is transform classical finite element codes into immersed codes with minimal implementation effort. And the primary technology underneath this is interpolation-based immersed FEA. So let me introduce what this is now. All right, so I have to show some math, for better or worse. Okay. So to ground everything, I'm going to talk about a very simple model problem. So I'm going to consider the Poisson problem over this potato over here. I'm going to call that potato omega, the boundary of the potato, partial omega. And I'm going to consider a pure Dirichlet problem, right? So U equals G on the boundary of that potato, right? So to construct a finite element method, right, we first have to construct a weak form, right? So we have to construct an appropriate set of trial functions and test functions, right? And what I do then is I take my PDE, I multiply by a test function, integrate over the domain, integrate by parts, right? And then typically for a Dirichlet problem, I'll set the value of my test function to 0 along the boundary and the value of my trial solution to G along the boundary. And that gives rise to this nice problem here, right? And then you can approximate these infinite dimensional spaces here with finite dimensional spaces of finite element functions, giving rise to a matrix problem I can solve, right? For an immersed method, we have roughly the same thing, except for we cannot enforce those boundary conditions strongly, right? It's hard for us to set, for instance, our test function to 0 along the boundary without losing accuracy. So what we do typically instead is enforce those boundary conditions weakly, and we use something called Michie's method. So that gives rise to these additional terms here, where this term here is the term that results from integration by parts if VH is not 0 along the boundary. You then add in a couple of other terms. This term here, notice that it multiplies UH minus G. So for the exact solution, this is 0. If this sign is chosen to be minus, what this gives rise is to a symmetric bilinear form. So it gives rise to a symmetric stiffness matrix, which is nice. And then you get this penalty looking term that's more strongly enforcing the boundary condition, where H here is a mesh size, right? And alpha here is just a constant that you can tune. And typically you choose it to be big enough so you enforce the boundary condition some way. So with the quadrature-based immersed method, what you do is you define your function space on that background mesh. Pretty simple. Use standard element Gaussian quadrature on the cells contained in the domain. And then you have to integrate over these cut cells. And let's just consider the solution of meshing, right? It could be a poor quality mesh, right? So then what we do is we tessellate these mesh cell intersections with quadrature elements, and this will form what I'll call a foreground mesh. So we have the background mesh here, right, that we define our basis functions that we're going to use to approximate the solution. Then we're going to have this foreground mesh. And then we can use standard Gauss quadrature on the elements of the foreground mesh. So in mathematical notation, what you end up doing is you end up replacing, right, these integrals over the full domain by the sum of integrals over the foreground elements, right? But this then leads to the implementation problem I talked about earlier, where the quadrature is defined in the foreground mesh, but the basis functions are defined in the background mesh. So you can't use standard FEM data structures and assembly algorithms. So this led us to say, can we use basis functions that are defined on the same mesh as the quadrature on the foreground mesh for assembly, right? And the answer is yes, but you have to perturb things a little bit. And the approach is really quite simple. You first just define a nodal basis on the foreground mesh, so a Lagrange basis, right? I'll refer to the basis functions as phi j and the nodes as xj. And this could be element-wise or it could be globally. And you just interpolate the background basis functions in that foreground space, and then use the span of those interpolated background basis functions as your solution space. And in doing so, what we've actually done is we've changed the background basis functions from what they originally were to some interpolation. And then it turns out this is equivalent to the aforementioned quadrature-based method if the foreground mesh is fitted to the background mesh. What I mean by that is every foreground element lives within a single background element. And second of all, the foreground basis can exactly represent the background basis. But we can actually relax these things. And this gives rise to new numerical methods. For instance, we can reduce the polynomial degree of the foreground basis, or we could even use a background unfitted foreground mesh, which gives rise to more flexibility in mesh generation, avoiding, for instance, small cut cells and the like that are oftentimes problematic in immersed methods. And you might ask yourself, why would you want to do this? So if you consider, for instance, a tensor product element, if you have a background basis that's quadratic, it's actually biquadratic. So that actually means that the degree of the polynomial is 4, not 2. Using this, if we are using triangles for integration, that allows us to use degree 2 rather than 4 to represent the full function. And to give you an idea of what's really going on, consider this case we have a domain in red, a background mesh in black, and suppose that we're going to use background basis functions that are C1 biquadratic B-splines. Up top, we've got a background fitted foreground mesh, and on the bottom, we have the background unfitted mesh. And you can see what we get if we use linears and quadratics on the foreground mesh for approximating our basis here, right? So you can see that with the quadratic, we get something that's visually indistinguishable from the original B-spline, even though we don't exactly represent cortex, and therefore these basis functions are actually approximations, not the original basis functions. Now, how does that actually help you with implementation? Well, the discrete problem that we really want to solve takes the form KD is equal to F. You've taken finite elements, right? K is your stiffness matrix, F is your loading vector or force vector, where the ijth entry of our stiffness matrix, Kij, will simply be our bilinear form that we have, right, evaluated for the jth and ith interpolated background basis function. In Fi, we have this linear form on the right-hand side, will be that evaluated for the ith interpolated background basis function. Now, what is easy to assemble over the foreground mesh with an existing finite element code like Phoenix is Ai, Ij, and Bi, where we basically swapped out our interpolated background basis with our Lagrange basis. Right? This is what already is in your code. But it turns out that I can represent my n hat i's and my n hat j's in terms of those phi i's using an interpolation operator. And we can do this globally, or we can just do this element-wise. So that means that either element-wise or globally, K is M transpose AM, where M is this interpolation matrix, and F is M transpose B. So if you can construct A and B, you can construct K and F immediately. And the only non-standard assumption here is that the existing finite element code can implement AH and LH for Nitsche's method. So that's turns out the hardest part of all of this. And you can actually show for background fitted foreground meshes and under various technical assumptions, you have an interpolation bound, you have a best approximation result that says that your best approximation error is bounded above by C times H to a power K hat times the usual thing, a Sobolev norm of U, where K hat is the minimum degree of polynomial completeness between the background and foreground function spaces. So this gives rise to some guidelines for what you should choose the foreground degree to be, right? And as I already mentioned, the background space may have some polynomials or some monomials with degree greater than or equal to K, but you don't need to actually capture those in the foreground space for optimal order interpolation error. And numerical results actually show that this interpolation error bound holds under significantly more general conditions. And I'm working with some folks from Sweden to try to prove this. It turns out it's kind of gnarly. It's outside of the usual purview of mathematical finite element analysis, mathematics of finite analysis. So just to show you, for some very simple problems, does this work? So here's just a 2D Poisson problem with a background fitted foreground mesh. And what I've got on the left column is measure of L2 error versus number of degrees of freedom. On the right, H1 naught error, so L2 norm and H1 naught norm. In green here, we have original quadrature-based immersed finite element results. In purple, we have the interpolation-based. And in blue, we have traditional finite element analysis using the foreground mesh. And you can see that the interpolation-based is giving us optimal order of accuracy, and it's actually not very far off the quadrature-based, and it performs better on an error per degree of freedom basis. And it turns out the situation's better in 3D, as you might imagine. And that's due to the fact that our foreground mesh actually contains very terrible looking elements. So you actually have a lot more degree of freedom per error than you really would like. So you actually get a lot more bang for your buck in the 3D case. And you still, of course, get convergence at optimal rates. And it also works for the case of a background unfitted foreground mesh. So that was something I mentioned before. It's not something that you would normally think of, but here we've got this background mesh, right, which is this triangular mesh. And in the foreground mesh, we've got these triangles, right, these foreground triangles that are overlapping, right? If you try to use that for quadrature of a classical quadrature-based immersed finite element method, you would get terrible results. But using this interpolation-based scheme, we get optimal rates. This is outside the scope of our initial interpolation error analysis, and that's one of the things that we're trying to show. So one interesting thing is when you actually do this interpolation, you actually can reduce the smoothness of your background basis function. So when you start off with a C1 quadratic B-spline, and then you interpolate it onto this mesh using quadratic Lagrange, turns out the resulting interpolated background basis function is only approximately C1. So that means that it usually can't be applied to higher order PDEs, such as the biharmonic problem, Kirchhoff-Love plates, et cetera. But what we find is we still get optimal rates of convergence, where here the H2 error has to be thought of as a in terms of a sum over elements rather than a classical H2 norm, because our interpolated background basis doesn't actually live in H2. So it still works. This turns out is the hardest thing to try to prove anything about. So we're working on it, but it was extremely surprising. And then you can apply it, for instance, to fluid flow problems. Here I'm going to look at equal order elements with VMS stabilization, which if you look at this term here, Rm is our momentum residual. Tau m here is this stabilization parameter, and this is, if you know anything about finite elements, this is SUPG plus PSPG stabilization. I don't want to go into the details here for the sake of time. And here is grad div stabilization. And here are some non-standard terms that you get through the VMS, residual-based VMS framework. And here are terms that are responsible for weak enforcement of boundary conditions. So if you apply this to like a simple Taylor-Green vortex problem, you can see visually it looks right, and you get the right rates as well. Now, what's fun about this is then you can start to apply it to other interesting problems. For instance, you can look at image-based analysis. right? For instance, of composite materials. So here we're looking at linear elastic analysis of alumina particles embedded in epoxy. And here, the only definition of geometry that we have is from a micro CT image. But using this approach, if you can generate a level set from this, you can then perform analysis. And here, I'm actually leveraging local adaptivity of both the foreground mesh and the background mesh using hierarchical B-splines. You can see that the results between the immersed finite element analysis and body finite element analysis and von Mises stress are indistinguishable. And if you zoom in, where you're having this peak von Mises stress, you can really see that you're actually nailing it without having to generate a high quality mesh. And you can apply these ideas as well to multi-physics type problems and multi-material problems. So here is an example of a thermal elasticity problem where you have heating of a plate with an inclusion. And here you can see on the left is the interpolation-based immersed isogeometric analysis result versus the quadrature-based result, and they're indistinguishable. And just for a fun little picture, here's just interpolation-based trimmed isogeometric shell analysis. And here what we've done is we've got a background discretization that's just tensor product. We're going to cut out this thing here, and then we're going to actually map it onto thing, and then we're going to pull on that tab. And we're going to solve the nonlinear Kirchhoff-Love shell equations to actually look at the deformation of that tab with a follower load. And you can see that with both the background unfitted foreground mesh, this requires C1 continuity of your background basis. We actually have that approximately, but it's still giving something that looks physically right. And if you actually take a look at displacement of the tab edge versus a converged value obtained using a conventional isogeometric analysis code, it converges very, very quickly, and it's quite accurate. I should note all of those results were done in Phoenix in a few lines of code. We have some more interesting results using an in-house code. I don't want to show it because the whole entire point of this is to get your hands on code, right, and convert your own code at the end of the day. So in the time remaining, I just want to highlight, cool, this is all great. How can you transform classical codes into immersed codes with our software framework, with Exum? So what our software library Exum does is it creates foreground meshes, extraction operators, and connectivity arrays outside the confines of any particular finite element code. So you can think of this as follows. You've got some background discretization and geometry representation that you feed in. And what we give you is extraction data structures for unfitted finite element analysis. You can think of it as that big M that I talked about before, or you can think of it as I'm going to have a little m for each element in a connectivity array that tells you how local degrees of freedom map into global degrees of freedom. And then you can retrofit your existing finite element code, right? This will spit out an unfitted finite element solution. Then we interpolate that, and then we can give you an XML VTK file that you can read in a pair view and actually look at solution results. So that's the rough picture. And I'll demonstrate here in a minute that we've leveraged these extraction data structures to transform Phoenix in an interpolation-based immersed code. So I'm going to skip the details here, but just in terms of essentially what we provide here. So this is a software library called Morris. And Morris actually was developed for XFEM-based level set topology optimization. What we did is we retrofitted the code so that it could just provide the data structure so you can convert your own code and use those data structures. So what Morris has is a geometry engine, right? And this defines the geometry, and this basically handles the level set fields. And then we have a hierarchical background mesh generator that defines the background mesh and the basis. And then this immersed finite element toolkit, XTK, generates the foreground mesh using a templated approach. It's not guaranteed they're going to have a high quality mesh, but you don't care. And it computes the extraction operators, and that's what it'll return for you, right? So what we can do right now is we can handle user-defined level set fields, predefined geometries, 2D, 3D image files, STL files with closed surfaces. We can actually handle hierarchical B-splines. So we can actually handle B-splines with local refinement and classical finite elements for your background discretization. And then XTK, as already mentioned, generates the foreground mesh that you need. All right. So how do we leverage Phoenix here? And this is actually where I want to finish here. I've got some other slides I can point to a little bit later if you're interested. So the Phoenix project, so Phoenix is an open source software tool chain that automates the compilation of finite element code. And what basically allows you to do is express variational forms like this in terms of this very simple language, UFL. So A is equal to dot grad U and grad V times some volume measure. And essentially what this does is it assembles a system of algebraic equations from the variational forms and discretizations for a number of different finite elements, in particular classical finite element analysis. And the way that we were able to do interpolation-based immersed finite element analysis is we assemble A and B using what's already in Phoenix, compute this, solve, project, visualize. Super simple. And just to show you how simple this is, so this is solving the Poisson problem with classical FEA in Phoenix. So it's also a little bit of a pitch. It's nice that you can just write a few lines and get this in. So this first bit is just loading a mesh and defining subdomains, defining a classic finite element function space in your variational problem, and then force boundary conditions and solve. Right. So here it's doing this strongly. Now, in order to do interpolation based, you need to load our module. It actually doesn't have too much in there. Enforce boundary conditions with Nietzsche's method, which just are a few additional terms in your variational form. Right. You can compute A and B, right? So that's your JF and your residual here. And then you transform your matrix system, linear solve, output. And that's it. So that was actually quite nice. So for the sake of time, I can touch on this real fast. I want to go more than 3 more minutes. So what are some current capabilities of the code if you're interested in using this? So we have support for locally refined mixed foreground meshes of tris, quads in 2D and tets, hexes in 3D with hanging nodes. And hanging nodes are not a problem at all. So this enables us to really refine along geometric boundaries in a simple way without having to do a lot of mesh topology operations. As previously alluded to, we have support for locally refined background discretizations using hierarchical B-splines. And the basic idea is you can take a B-spline basis, you can refine once, you get a refined B-spline basis, you can refine again, you get another B-spline basis. And instead of refining the mesh and defining your new basis with respect to that mesh, instead what we do is we say, hey, we want some of the functions from those finer levels to be active. And then by recognizing the fact that we can represent basis functions on coarser levels in terms of basis functions on finer levels, you can remove functions where there's linear dependencies. And in doing so, we end up with a basis with local refinement capability. And then we use this operation called truncation to restore partition of unity. So that's something that you lose in the process. You don't actually end up changing your space at all. You just change your basis, but this actually results in reduced support size of your basis function, which then also results in sparser stiffness and tangent matrices for nonlinear problems. For multi-material problems, it turns out that you don't just want to use the background basis as is, right? Because, for instance, if you've got a heat conduction problem, your thermal conductivity is different between these, right? The heat flux in the normal direction will be continuous across this interface, but because the thermal conductivity is discontinuous, that means the gradient of temperature in the normal direction should be discontinuous. So you actually want to build in that discontinuity in some way. So we use this heaviside enrichment to have separate interpolations into different material subdomains. And that actually is pretty important for performance. The user doesn't see it, it's hidden in M. So that's the really nice part. We can actually allow for separate background discretizations for multi-physics problems. So we can actually have different discretizations for displacement and temperature, for instance, that you may be interested in. And it turns out one big issue with immersed finite element analysis is you end up getting instability in the presence of small cut cells and actually condition number spikes. And there's a variety of different solutions that you can utilize to address this issue. And one that was actually introduced this year is particularly nice for us, which is actually we end up changing our basis a little bit. We end up removing bad basis functions. So those are basis functions who support with the that intersects with the physical domain is only over slivers. We remove those and we actually modify the remaining basis function so that you get back polynomial completeness and partition of unity. And it turns out, from the user standpoint, that just means you have a different M, a different connectivity array. So this is, again, transparent to the user. So it turns out you don't have to do anything on your end if you're going to try to transform your existing code. So plain capabilities. So support for curved integration elements is currently being implemented, as well as BREPs, hopefully. Turns out that's gnarly. And we're also equipping Exum with the capability to generate and output cut cell quadrature rules if you just want to actually modify the quadrature rules inside of your code instead of use these extraction operators. All right, so some useful links, and I'll just keep these up here. So here's a link to our Morris Exum software library and our Phoenix implementation. But the one I really want to highlight here is we had an Exum collaborators workshop a few weeks ago where we actually have tutorials to our code and a lot of other things. So that might be useful if you're actually interested in picking this up in terms of installing and running stuff, things like that. So there's a QR code. And I was going to say thank you. Those are sponsors. I'll leave that there. Yeah, sure.
So like when you have coefficient,
yep.
So like how does that work in practice, and like how stable is it to the values you actually need to use, right? It's going to become more stiff as you increase that. So.
That's correct. So it turns out there's different flavor of niche use methods. If you notice, kind of going back to that slide, and let me, rather than do a flurry of slides at you, I'll just scroll back. Notice that there's a sign change here. If you use a minus sign, then you end up with a symmetric stiffness matrix. And what you need to do is you need to choose alpha sufficiently large so you end up with a positive definite system. And it turns out there's actually trace inequalities that you can actually leverage to come up with what alpha should be. And turns out there's explicit formulas in terms of polynomial degree, et cetera. In that case, if you have small cut cells, turns out alpha blows up to infinity as your ratio of your cut cell volume over the actual cell volume goes to 0. But if you use the stabilization approach that I mentioned at the end of the talk, it turns out that is not the case. So it turns out you can use relatively moderate values of alpha, 4, 10. For splines, it ends up being like 4 or 10 ends up being a great option, pretty much all cases. If you choose plus instead of minus, it turns out that any value of alpha will work. It's stable no matter what. This gives rise to what's called the non-symmetric niche method. So you end up with a non-symmetric stiffness matrix. So you can't use, for instance, conjugate gradient method, but ends up being stable. Excellent. Yep. Cool. Oh, there's 2 in the back. Yeah.
Thank you very much for the great talk. Does the current architecture support differentiability with respect to the parameter since I'm really interested in implementing this for some kind of optimization problems. So I was wondering if it is possible to propagate the gradients across this architecture.
Sure. So that's something that we're working on this next year. I always like to say, yeah, we'll do it eventually. To be honest, I think that the challenging part there is making sure that your finite element code can compute the sensitivities that you need, right? And if your code can kind of compute sensitivities with respect to your foreground mesh, you can leverage chain rules and be able to compute sensitivities with respect to your actual shape parameters that you happen to have by knowing how the foreground mesh depends on the shape parameters. That's what we will be providing to users as well as that sensitivity. Then if you have those 2 objects, then you can progress forward. Right now, the code base doesn't provide that information, but that is something that we're planning for. The code base actually has that capability. It is an optimization code, ultimately. We just haven't returned that for users to use.
So your slide, the first slide.
Yeah. That's right. So, because it's magic. So you're talking about this slide? So in this particular case, we're not using a great finite element mesh. We're using the foreground finite element mesh. The one that we can compute very quickly, and using that for classical finite element analysis. Now, if you're using that foreground mesh, you're actually going to have additional degrees of freedom because you're actually refining quite a bit when you're doing that. So the idea here is when you cut here, right? Right. Right. So we're using that foreground mesh purely. So if you think about it in terms of the math notation I use for linear algebra, it's like you're computing AD is equal to B rather than KD is equal to F. And then you're using that foreground approximation purely. It turns out that when you use that interpolation matrix M, essentially what you're doing is you're going to a subspace, right? So from the standpoint of number of degrees of freedom, you're reducing the number of degrees of freedom. So it's like bringing your curve to the left at the end of the day. And you can see in 3D, the effect is more dramatic. Thank you.